All right, it's 12 noon. We should get started. I see our Dean of LAS, Andrew's here. Andrew, did you want to give the intro? Because quite often the intro is done by the Dean's office.
Well, I mean, I will. I'm very, very pleased to see Carlo Rovelli here. I believe he's zooming in from Canada. I don't know if I got that right. Good. And this, as you know, this is Watkins, a wonderful, generous gift allowed us to have a series every year, and we've had it for many, many, many years. One is a very technical talk, which I know is coming up in physics. This is meant to be more accessible for people like me to understand what's going on. And I have to say, Carlo, your topic looks absolutely fascinating. So I don't want to get between you and the topic, so I will stop talking. But thank you very much for coming. Normally, I would say, Carlo, also is tonight we would take you out for a very good dinner. So unfortunately, I know. Maybe one day in the future we'll invite you back.
And that leads me to a very important point that the Watkins physics talk every year is a very important event on campus because we get to bring in a very good speaker. And with the pandemic, we didn't want the opportunity to pass by this year because then it would give students less chance to interact with someone outside our own community who's extremely exceptional. And so we wanted the speaker who would be really fantastically great. And Forbes magazine lists Carlo Rovelli as in the top 100 most influential thinkers alive today. And his topic of quantum gravity and if things really exist or not is a wonderful subject. He's actually written 4 books for the public, one of which is I'm very envious of because he has had one of his books translated into 41 languages. I only have mine in 7 languages, one of my 2 books for the public. And I saw the number 41. I was like, wow, that's a lot of books. And by the way, 2 of mine are actually pirated copies in Polish and Chinese. Anyway, he's going to give us a talk today, which is designed for the public, making sense of the quantum. Do things exist by themselves? So I'd like to ask everyone to mute their speakers, except for Carlo, and welcome.
Thank you very much. And thank you all of you for being here. Thank you, Andrew. Thank you, Nick. Thank you for this invitation. I look forward for the moment in which they will sort of open the cages again and I can travel and I'll be there in person. I hope this will happen. I'm going to give, yes, this talk thought for a larger audience, and the day after tomorrow a little bit more technical talk on quantum gravity and black holes and white holes. But today I decided to talk about about quantum mechanics in general. The reason is that I think that quantum mechanics is a absolutely major scientific revolution compared to Copernican revolution or to Einstein revolution about space and time or to Darwin, these kind of things. But it is far, unlikely the others, it's far from absorbed by culture and even far from being absorbed and digested by the scientific community itself. Quantum mechanics is still an open problem for many scientists, not for all, for many scientists and for many philosophers, what exactly it means. So I've decided to sort of give an overview of where I think we are about quantum mechanics, saying where is the mystery, why many people think there is a mystery, some people think there is no mystery. And among the solutions or a tentative solution discussed, the one illustrate the one I find more convincing. So the presentation will have a part which is more general, and a part which is more specific on my own take on the subject, of course. So the title, it's Making Sense of the Quantum, and the subtitle is a little bit cryptical. Do things exist in themselves? I hope I'll get you to see what I mean by that. And let me just allow me to say that I recently published a book. It's out in the UK, but not yet in the US, on this topic. So to a little bit, I will follow the book. Not much, because the book goes into many aspects and many connections of quantum mechanics. Here I want to try to give you the main gift of the main idea, the main sense of what is the mystery of quantum mechanics, and what I think about it. And let me start sort of historically by the title of my book is Helgoland, which is nobody is supposed to understand what it is. Helgoland is this island here. This is an island in the northern sea between the UK, Denmark, and Germany. Now it's German. It has been Dutch, has been English in the past. You know how Europe works. And it's as you can see, it's rock. This is a picture in the taken in the 20s when the story I'm going to tell begins. It's rocky. It's with little vegetation. It's very small, and it's pretty wild, windswept. Not a place you would think you go to vacation, but this guy went into vacation there. Well, not really vacation. He was suffering hay fever, and it was a perfect place, Helgoland, to go because there's no vegetation, so to heal from this hay fever. And he went there also because he was immersed in the problems of the atoms. We are in 1925, and the guy is Heisenberg, Werner Heisenberg. And shortly after, he basically comes back with a calculation that he published in this paper here. You see, it's dated July 25. I don't know if you see it. And this is the paper where quantum mechanics started. Quantum mechanics is a collective enterprise. There's a lot of pieces of it that were put together before this paper. There are a lot of ideas that came before, from Einstein, from Bohr, from Niels Bohr, from many people. But everybody was confused up to this point, up to 1925. And when he wrote this paper, suddenly things start moving, and the paper is striking, is absolutely striking, because it has a new way of doing calculations and a new idea about science. So it's really the turning point from which quantum mechanics comes out. And I think all the people listening have an idea of quantum mechanics, but let me just say, because I don't think anybody can underestimate quantum theory, the power of this incredible theory, which is quantum theory. First of all, that was 1925, so we're 100 years ago. And so quantum theory is it's 100 years old. It has never been found wrong. I would say it's the only theory in physics we know that has never been found wrong. It's been surprised everybody by its prediction being all right or correct. And more than that, we have no hint of where it could go wrong, because there are other theories which have never been found wrong, like the standard model of general relativity, for theory in fundamental physics. But we know where to expect that they would not hold anymore. General relativity is not going to be good as soon as there are quantum phenomena, in fact, and the standard model is most likely not going to be correct as when we go high in energy. Quantum mechanics, we have no hint of that is go wrong. It may go wrong somewhere, of course. Some people are doing experiments to see whether it go wrong, but as far as we know, it's so far it's a perfect theory, so to say. It's a very general theory. It's like classical mechanics, so it can be applied to all sorts of systems. And the effect on science that it has had and on technology, it's immense. A lot of modern science uses quantum mechanics. Computer use quantum mechanics. The semiconductor, the chips, the basic electronics is using it's computed using quantum quantum mechanics and use quantum phenomena, lasers, magnetic resonance, nuclear power, nuclear bombs, all sorts of things. And it's fundamental to understand things like how the sun works. This is a picture of the sun, how galaxy formation. Recently, there is a quantum mechanical theory about the structure formation in the universe. And perhaps the most spectacular thing is chemistry. The basic of chemistry, which is a periodic table of elements, is just completely accounted for by an equation of quantum mechanics. So this is a spectacular theory that come out from an idea of this guy, Heisenberg. And what did he have in mind at the time? I'll try to illustrate what is the basic idea he has and he had. But I want to stress that in his mind, there were a variety of things when he came out with this idea. First of all, there was all the problems of the atoms and the early quantum theory, sort of the attempt to go toward this quantum theory that were very confusing. The work of Niels Bohr, who had already done Nobel Prize research by coming out with a sketch of a model of an atom that worked to some extent, but not completely. Heisenberg went to work with Bohr and was hiking in the mountain with him, discussing with him a lot. So there was all this physics, but there was also a lot of philosophy in his mind. And in fact, his article is almost a citation from Ernst Mach, philosophical work. And I'll tell you what the citation is in a moment. And there was poetry. He was in the island, basically doing calculation and reading Goethe, German poet, of course, perhaps the greatest German poet. And in fact, he was learning by heart poems from a collection by Goethe, which is the East-West Divan, which is a collection of poems about Islam. Goethe was in love with Islam, and in particular Persian Islam. And this is a collection of poems in which he basically sings his love for Islam and Islamic culture. And it is really an enlarging perspective with respect to sort of Eurocentric intellectual world of the early 20th century. So Heisenberg has all this in mind: physics, philosophy, poetry. He comes back from the island with a calculation, which very rapidly gives rise to this paper here, and then with a group of friends, the 2 or 3 papers in which they are published together, one by Max Born, which is his senior mentor and senior professor. I mean, he was an assistant, Max Bohr. So one paper is by Max Bohr, and another young kids at the working with Bohr, with his Pascal Jordan, and then a paper by the 3 of them. And then Wolfgang Pauli uses their results for computing the spectrum of the hydrogen atom. And independently, Paul Dirac reads this, the first paper by Heisenberg, and come up with the same theory as these guys here. And this is quantum mechanics. And I have the paper I showed you here. It's a remarkable copy of it, because you can handwritten here is handwritten. What do you think about this? This is Fowler, the professor of Dirac, who received this copy and gave it to Dirac, saying, what do you think about this? And Dirac read this paper and wrote one of the main papers on quantum mechanics. So this is exactly the copy that Dirac read of the paper. We are in 1925, and the theory is essentially completed. This is a paper, Suche Quantum Mechanik, by Bohr and Jordan. They of course mention Heisenberg, and what they take out from Heisenberg calculation, which is a basic of quantum theory, is something absolutely spectacular. So basically, they say we can understand better the world if we use the same equations as classical mechanics. So the same equation we always use, the same forces, the same electrical force in the atom between the electron, which is negative, and the nucleus, which is positive. But we describe quantities not as number, but as tables of numbers. Mathematicians call matrices. And since table of numbers can be multiplied, but if you multiply A times B, you get a different number than B times A, you use the same equation as before, but you have one extra equation that tells you this one here. Let me put it larger, which tells you if you multiply two things in one order, PQ minus QP, what the difference is. And here, Q is a position, say, of the electron, and P is the velocity of the electron, multiplied by the mass, the momentum. And so this is the only new equation. All the rest is the old equation. So this is a single equation from which, you know, atomic bomb, lasers, understanding the sun, but everything comes out from that single equation, so to say. So this is the strange novelty, mathematical novelty. Just replace quantities like velocity or position with tables of numbers, and everything comes out. So this is quantum mechanics in 1925, written by these people here. So Heisenberg, Born, Jordan, and independently Dirac. So the mathematics is the same equation plus one. And then there are some instruction of how to use this equation and the philosophy. And the paper by Heisenberg, that paper that I flashed before, opens up. I am not going to read the German because you will laugh if you know German for my reading the German. But it opens up under the influence of Mach philosophy by saying, I'm going to introduce a new mechanics, essentially, where instead of using a variable to describe system, I only use the quantity that can be observed. And that's a key point. This is the strange novelty. These numbers do not represent anymore a property of a system, but something related to observations. And in fact, these matrices that come out in in this new mechanics, each entry of the matrix corresponds to one possible observation. Let me jump back to the picture of what was in Heisenberg's mind. Here it is. The physics of the atom, as was understood by Bohr, is that the electron can only stay on some particular orbits around the nucleus and can jump from one to the other. And when it jumps, it emits a photon, and we see the photon. We see the light from the jumps. And these matrices are the on the rows here are the starting orbits, and the columns are the arrival orbits. So each entry is a particular jump, which means one of the things we can see. So it's not the position, say, of the electron, but it's what we can see about the position, the ensemble of things we can see about the position. So that's the novelty. The theory talks about observations, not about what happens. What it gives is a probability that we have one observation given another observation. And that's a mystery, because what does nature know about we being observing or not? So in other words, why don't I can describe the atom by itself, and I have to describe what I see about the atom, the particular effect of a jump of the electron from one orbit to the other. It's like these classical mechanics, of course, can describe what we observe, but we don't have to think about anybody observing. It describes how something moves. A pendulum is oscillating, and it describes where it is at every moment. Quantum mechanics doesn't work this way. It describes, if you look at the pendulum, see something, then it gives the probability that you're going to see something else. And in between, it doesn't say what happened. Now, parenthesis. This is 1925. 1 year later, there is a important development, which is the work by Schrödinger in 26, Erwin Schrödinger, which, inspired by some ideas of French aristocrat Louis de Broglie, who had written a strange thesis claiming that particles are waves, Schrödinger writes an equation for a wave, the famous wave function, or quantum state of quantum mechanics, where everything seems to be explained, because now the electron moving around in the atom around the nucleus, it's represented by a wave. So it's like, you know, the oscillations of a lake moved by, and this equation here, which is a famous Schrödinger equation, this equation here it's an equation that the wave satisfies. And everybody seems very happy because physicists understand waves well, like waves in the sea, electromagnetic waves. They're used to wave equations. So instead of these strange non-commuting numbers and matrices, now we have waves. So for a moment, it seems that the strange mystery of Heisenberg and Bohr and friends about observation is just wrong, and what is really happening is that particles are wave. But this is more smoke in the eye than clarity, because soon Schrödinger himself is able to show that the two pictures of quantum mechanics are actually mathematically equivalent. But more importantly, the wave itself is not a wave. It's understood by Max Born, in fact, that what it gives is a probability for something to happen. So it's not really a solution of the problem. If anything, it's a reformulation of the problem. Let me give you an idea of why. Suppose I have a radioactive atom here, and I have a detectors that detect the radiation, and I have a number around of this. So what happened is that at some time, one of the detectors clicks, Geiger counter, click, okay? And the way we compute it in quantum mechanics, if we use the wave, is to imagine that there is a wave produced by the atom. It goes all around, and so it's everywhere. If you solve the Schrödinger equation, and then at some point, one of the detectors clicks, and the wave disappears all over, and now it starts again where the detector has clicked. So it's still the observation by the detector that creates what we observe. So using the Schrödinger wave doesn't take away the mystery about observation, it just displaces them. And in fact, the one who understood this more clearly is Schrödinger himself. I have here, oops, no, sorry. This is out of order. Here's Schrödinger himself explaining that very clearly. Schrödinger years later, he said there was a moment in which the creator wave mechanic himself nurtured the illusion of having eliminated the discontinuity in quantum theory, but the discontinuity eliminated from the equations of Born and Heisenberg and company, reappear in the moment the theory is confronting with what we observed. So once again, it's observation. And Schrödinger himself ended up by writing things like the gaps eliminated from the wave picture have withdrawn the connection between the wave picture and the observable facts. And it is better to regard a particle not as a permanent entity, not as a wave, but an instantaneous set of events when the particle is observed, so to say. There's one way of before going into the possible solutions of this confusion. Schrödinger himself has a very famous fable in which he presents the mystery of quantum mechanics, which is a famous Schrödinger cat. There is an atom, and the wave function of the atom, this wave can split like the radiation can go all over. Imagine that it can split in two parts. And in the parable or fable by Schrödinger, there is a cat that in one case is so say this atom breaks a little bottle with some drug, and in one case the cat gets asleep, and in one case is still alive. So the cat is both asleep and alive, like the radiation of the electron is all around at all detectors. And when I look at it, I just see one of them. So the question is, what is really happening? Is the cat really in a superposition? How would the cat feel in this superposition? Or how would you guys feel if you were in a superposition of two things? Where is an electron if it is a superposition of two things? Given that every time we don't see a superposition. We see only the electron at one point. Every time we look at the cat, we see it either awake or asleep, not both at the same time. So the possible solutions of this story are many. And here is the list of possible ways of thinking about all that. I'm not going to describe all of them in some detail, but I'll just say a word about all of them. One way of thinking about quantum mechanics, which is common about certain category of physicists, is more or less to ignore the problem and say, well, why do we have to worry about what happens when we're not looking? After all, we have a measuring apparatus, and there's a quantum system, and every time we measure it, quantum theory tells us exactly what we're going to see. So if I have to build a computer, my little chip is a quantum thing. I know what goes in, I know what goes out, and the quantum theory tells me that. That's everything I know. There's another perspective on that, which is, well, forget the apparatus, because the apparatus itself can be a quantum theory. But after all, it's always a human, somebody who knows, who makes predictions, who uses quantum mechanics. So quantum mechanics is about what a subject of knowledge can say about what he sees about the world. A different way of reacting to all that is to take the wave function of Schrödinger very seriously. And there are various ways of doing that, three main ones. One is called many worlds, to think that what is really out there is really the wave function, not the cat. Another one is that there is a wave function, but there is also the cat. So if in the case of the electron, there's a wave, but there's also the electron. That's why we see the electron, because the wave is only guiding the electron. And then there's also another hypothesis that the reason we are confusing is that the quantum mechanics, it's wrong. And as it is, it's really incomprehensible. We have to correct it, and there will be some extra physics that modifies the Schrödinger equation, making it more substantial. I'm not going to talk about that. I'll talk about the interpretation of quantum mechanics by itself. Let me illustrate these various ways of thinking in case of the cat, right? Many worlds. This is one way of thinking, is that the wave function is the real thing. So really the cat is in superposition of two positions, because it's this quantum state that matters. So why do I see the cat only awake or only asleep? Because I am also described by a wave function. So my own wave function, when I interact with the cat, has going to have two components. So like the electron can be here and there, I can be in one way or another way. And in one way, I see the cat awake, and the other way I see the cat asleep. So there are really two of me. So why is he only one? Because I am one of the two. I'm going to be this, or I'm going to be this. In this case, I'm going to see this. In this case, I'm going to see that. So this is coherent, it's consistent, and it's one way of making sense of quantum mechanics. It's pretty popular among some cosmologists and some philosophers. The Oxford philosophers now are all enamored of this way of thinking. And some cosmologists, some very, very theoretical physicists like that. It's consistent, but then if this is so, quantum mechanics is telling us that there are copies of ourselves, real copies of ourselves, not just two, but zillions of copies, millions of copies of ourselves that see the world a little bit different. And we are just one of the many. This is an astonishing conclusion. I don't like it because I think it's not needed to go to believe in such outwardly conclusion that each one of us is just a copy of zillions of ourselves sitting in this immense wave function that contains many worlds. That's the name of the interpretation, many worlds. But that's one possible way of making sense of quantum mechanics. Another possible way of making sense of quantum mechanics is to, it's so-called pilot wave or Bohmian mechanics or hidden variables, which is the idea that there's a wave and there is also the particle. So there is a wave that describes the cat, but there is also the cat. So the cat is in one position, but there's another empty wave, which is needed because without this, the prediction would go wrong. So also there is there's a wave function with many copies of ourselves, but there's only one of these is real. It's the one where we are sitting, and it can be either this or that. And this is also a consistent way of quantum mechanics. Also has difficulties. It breaks Lorentz invariance. It has many reasons for which physicists don't like it. And in a sense, the idea is to multiply the entities out in the world beyond what we actually see, to sort of fill it up and reconstruct a classical picture. Another way, it's Cubism, and this is in the previous picture I've mentioned about many worlds, which is just a wave, and Bohmian, which is a wave and a particle, and Cubism is just one subject observing everything. And the idea of Cubism is forget, we don't know what's going on. The only thing we can talk about is what a subject can see. And basically, this is it. So it's a strong philosophical stance. It's a strongly anti-realist stance in a certain sense. Knowledge is only about what we know, and we cannot put together a coherent picture of the world at all. We only can have a theory that tells us, well, if I see this, I see that, and that's it. And if we try to feel what happens outside there, it doesn't work. See, whatever one does, one is forced to say something dramatic about the world. The last possibility is physical collapse, which is the idea that the Schrödinger equation is actually wrong, and it's not true that a macroscopic object like a cat is going to be in a superposition. There's some physical process at some point that breaks the linearity of quantum mechanics, breaks the fact that there are superpositions. So it's not true that out of an atom, the Schrödinger equation moves uniformly. There is some nonlinearity such that the Schrödinger wave concentrate constantly, which is of course a possibility, but it gives predictions different from quantum mechanics. And for the moment, all the experiments seems to be on the side of quantum mechanics. Quantum mechanics has always turned out right in all that. So this is a panoramic of the strange ways in which people today try to make sense of quantum mechanics in a number of different ways. But I want to focus on the one, this red one, relational quantum mechanics, which I've not mentioned yet, because after having worked on quantum theory for 30 years of my life or 40 years of my life and trying to use it for quantum gravity, none of these alternatives I find useful. And the perspective which I find more useful is the one which I'm going to describe in a moment, relational quantum mechanics. And to say what is the main idea, I want to go back to Niels Bohr, who has been, the guy who told Heisenberg all the problems of physics on which Heisenberg was thinking when he went to Helgoland, and has been the grandfather of quantum mechanics, the senior figure that all these kids who did quantum mechanics referred to. And he has always also been one of the deepest thinkers in the long discussions on the interpretation of quantum mechanics in the 30s when quantum mechanics was put together. And he has summarized his understanding of what is quantum mechanics about in one idea, which can be called contextuality, which he expressed in this way, is from one of his writings. In classical physics, the interaction between an object and a measuring apparatus can be overlooked, but in quantum physics, this interaction is an inseparable part of the phenomenon. So the unambiguous description of a quantum phenomenon is required in principle to include a description of all the relevant aspects of the experimental arrangement. Now, I think that this is the right point, but it's also misleading, this sentence. And it is what has been misleading the think about quantum mechanics for so long. Namely, it's all formulated in terms of apparatus experimental arrangement as if physics was only in the laboratory. But obviously, if we describe what happened on the sun or galaxy formation or a distant galaxy, there's no apparatus and there's no experimental arrangement. And today, 100 years later, we know that quantum mechanics works for all these things. Quantum mechanics has nothing to do with, obviously, with apparatuses or mind or physicists. So we should take the same idea, but take away the apparatus and the experimental arrangement. And this is possible by simply rewriting Bohr text in the following way, just generalizing it just slightly, which is the following. In classical physics, the properties of an object are determined irrespectively from the interaction between this object and the others. Quantum physics is a discovery that the interactions are inseparable aspect of the properties. So in other words, properties of an object do not pertain to the object itself, are a description of how the object interacts with something else. And therefore, the ambiguous description of any object requires the inclusion of all the other objects involved in the interaction in which the object manifests itself. So in other words, the relational interpretation of quantum mechanics is an attempt to make sense of quantum mechanics by not thinking about observations. Observation is what a human does, or a living being or a consciousness does, and replace observation with interaction. Interaction is what any two systems do when they affect one another. Two stones that hit one another, a photon that arrives on a screen, a particle in the sun, a proton in the sun that merge with another proton to give rise to helium, and so on. And to replace the notion of observables, which has been so dramatically central in the formulation of quantum mechanics, to a much more general notion, which is relations. So the observables, it's a quantum mechanical name of the variables of something. And instead of thinking of the variables of what I can see, just think of the variable as the quantity that describe how one object interacts with another one. And if we do that, quantum mechanics again becomes coherent in the following way. So this is a quantum mechanics of Bohr and Heisenberg and company. The math I said what is, the physics is just the physics of variables, but variables represent interactions and therefore are relative to the systems in interactions, which means that a variable relative to something doesn't necessarily imply that it is also relatively to something else. So let me go to the cat, and this is the relational answer to the issue of the cat. When the cat interact with the atom with respect to the cat is in either one of the two possible states. So the properties of the atom relative to the cat are determinate, but they're determinate relative to the cat, which does not imply that they're determinate relatively to another physical system, which is not interacting with the atom or the cat at that particular moment. So if at a later time, another system physical system, observer, or whatever, interacts with the cat, with the system formed by the cat and the atom, the fact that the atom had a property with respect to the cat does not influence the effect of the interaction of the atom or the cat on the system here. So what is relative to the cat is not necessarily relative to another observer or another physical system. Now, if you do that, suddenly things make sense. So instead of measurement, we can talk about interaction. Instead of observers or apparata, we can use any system. We can view quantum mechanics as a description of how systems manifest themselves to one another in interactions. But we reinterpret physical variables not as properties of one system, but as relational properties between two different systems. So this is a pen with respect to me, is blue with respect to me, but it's not necessarily blue and oriented in this way rather than another way with respect to something else. Of course, it's in the classical world, things are gonna coalesce in a common picture, but not once we go to details, quantum details. Now, the key idea here is that there's been a long confusion in the users' observers in quantum mechanics, leading to interpreting it as a subjective picture of the world, okay? In fact, some people have tried to interpret quantum mechanics as using consciousness. It's consciousness that transform a wave function in a variable, in a precise variable. I think this is completely wrong. And the confusion is between relational and subjective. If I say that the moon has a certain velocity relative to the Earth and another relative to the sun, I'm not saying that the sun is conscious or the Earth is conscious. So I only say that some physical variables are relative. And so the quantum mechanics is discovering that all variables are relative and not that there is subjectivity anywhere in the way we describe physics. And if I have a minute, yeah, I can just take a minute. In the book, I have a couple of chapters that go out from the strictly physical discussion, because in the same years in which quantum mechanics emerged, there were discussion in the culture in Europe, which were parallel exactly to this debate here, and that reflect the current debate about subjective versus objective, realism versus instrumentalism in quantum mechanics. And perhaps the most interesting of that is the debate between Lenin and Bogdanov, who were at the head, the two heads, so to say, of the Bolshevik movement and party that led to the October Revolution in Russia. And there was a furious ideological polemic between them. This is Bogdanov, this is Lenin, the two of them playing chess in a very famous picture. This is in Capri. Gorky is the one looking at them, the writer, the Russian writer. And Bogdanov was under the influence of Mach, exactly like Heisenberg, and took very seriously this idea of Mach that we should rely on what is manifest without assuming a priori that there is a materialistic that our philosophy can tell us for sure what is matter behind these things. And Lenin wrote this famous book, Materialism and Empirical Criticism, against Bogdanov, against the Machian, as they were called in the discussion at the time, blaming them of idealism, saying you are wrong because you're reducing everything to the mind. And I think this is exactly the mistake that we make in thinking about quantum mechanics, reading it as if it was pushing towards subjectivity. Okay, quantum mechanics is about observation, therefore it's about the mind. No, because subjective doesn't mean relational. And in fact, the entire philosophy of Bogdanov, which is a fascinating philosophy at the root hidden root of a lot of contemporary thinking, including structuralism and similar, it's precisely realizing that there is a relational aspect in the way we think the world, which is part of the way reality is. And if we take too strongly, that's really what Marx said, if we take too strongly the strictly naive materialism of classical mechanics, namely, the world must be described by matter moving in space with properties, we are doing a philosophical mistake. We are confusing a step in our understanding of the world with a priori that our philosophy guarantees as correct. And when Lenin is saying, well, we know from science that the universe is just particles bouncing around, Bogdanov is saying, well, wait, this is 19th century science or 18th century science. 20th century science is more complicated. We should be open to changes. And changes does not mean that we are abandoning materialism for idealism. It means that there's nothing idealistic in quantum mechanics, and its instrumental readings, like in Cubism, are, in my opinion, making the same mistake that that Lenin is making. So confusing relationality with subjectivity. It's hard to find a philosophical grounding for quantum mechanics, and in my book I try to discuss some philosophers who insist on a relational perspective. There are many, but I don't want to go that in this direction. So here I think is the key. It's the key message of quantum mechanics. That's what we have discovered. So factor relative to physical system. I mean, this is when we say a system has a property, we're really saying a system has interacted with something else and the way it has affected something else is so and so. And if one goes in that way, in that direction, I claim quantum mechanics makes sense. Of course, there is a high philosophical price to pay. I mean, the world is not described by entities separated with property. The world is described by entities having properties relative to one another when they interact. Recently, there have been a lot of theoretical and experimental world work stressing a similar idea. This is a laboratory implementation of the Schrdinger cat, so to say. And I don't want to go into the details. I want to just mention the title. This is experimental rejection of observer independence in the quantum world. So the world, they say, the scientific method relies on fact, and they say, but facts are relative. Facts are not absolute. So the fact that a quantity has a certain variable take a certain value must be taken in quantum mechanics only as meaning that is interacting with something else. And in the moment of the interaction has this value. So once again, when the cat is and the atom are not interacting with the system, they have no value. This is the meaning of superposition. It's not that the cat is in two positions at the same time. It's that it is in neither because it has no value with respect to an external observer. All right, so I'll skip this. This is my sort of very short summary of the story. If we use quantum mechanics, textbook quantum mechanics tell us that in some strange way things are in superposition. Cats can be asleep and awake at the same time. In the many world way of viewing this is, well, there are two worlds, and the copies of us that split. The pilot ways are the hidden variables that somehow behind the screen rule what is going on. Cubism and related interpretation just say, don't ask what is going on for real, just ask only what an observer can detect. And relational quantum mechanics is that there is a deep relationality. The world with respect to the cat and the world with respect to another observer, the external observer, can be different. Of course, they're coherent once you go to the classical limit and you don't see interference anymore, and you lose all this vagueness, and the world stabilize in the classical limit. Okay, I go to the conclusion. I think that on the long run, realizing the relationality of the world is the way in which we might converge to make sense of quantum theory. But I also see that all these ways are coherent. Each one of them is striking, because quantum mechanics is striking. And this always reminds me of something that Feynman used to say, which is very useful, I would say, which is one of the amazing characteristics of nature is the variety of interpretation schemes that nature admits. And so, as Feynman said, they seem to be able to get through several wickets at the same time. And so what is the attitude that he suggests or recommend of that? Well, this is always Feynman. Every theoretical physicist who is any good knows 6 or 7 different theoretical representations for exactly the same physics. And so in a sense, it's not bad if we want to think deeply about quantum mechanics to remember that it can be thought in all these ways. And can all be thought by just ignoring all this and say, I'm in my lab, I just have my macroscopic world, and I know how quantum systems affect the macroscopic world. I don't ask what is going on. Does this mean that they're all equal? No, because Feynman goes on saying psychologically, we will keep all of them in our heads because I don't have here the continuation. We never know which one of them will prove useful and productive and fertile in the future. So I do think that we're going to converge to some way of thinking of quantum mechanics. And I expect that we're going to converge not by thinking that there are many copies of ourselves, not by thinking that there are extra variables, not by giving up the idea of making a picture about the world, because the first two are trying to squeeze quantum mechanics into a classical worldview by adding stuff. And the second is the extreme opposite. It's just giving up the idea of as objective as possible view about the world. I think we have to change our notion of what reality is. Reality is the interaction between things, is not separate things. So once again, this is a picture of everything. I have just a summary, vague summary here. I'm not sure is a good summary. Quantum mechanics is about facts or variables that take value between systems. The wave function is not needed for doing quantum mechanics. I want to insist that it's misleading to think about wave function. The wave, it's misleading. Heisenberg immediately came out when Schrödinger did his work saying, oh, come on, if you think about the electron with his wave, you just go in the wrong direction. It's true that it's more visualizable. It's sort of a German expression that Schrödinger was saying at the beginning. Look, I mean, we see what's going on, but visualization can be misleading in physics, right? The caloric, the heat, you can take a picture of heat, and you're led to think that it's caloric. And the Ptolemaic epicycles are easily visualizable, but they're both two misleading notions. I mean, you understand better if we forget the epicycles and forget the caloric. So quantum mechanics is about variables that take relative value, which can be described by the same equation of classical theory plus 1, xp minus px is IH bar, which means that the variables are a non-commutative spectrum. And so variables take various intersections. Values of variables are relatively to interacting system. And facts, we consider facts tables only because in the macroscopic limit, when there are many degrees of freedom, all this relationality disappears because we don't see interference anymore. So the physical content of quantum mechanics are two which are very well known: discreteness. I mean, light is made by photon and probability. Probability is fundamental, I believe. The world is not deterministic. And this mysterious contextuality, things have properties related to something else, which I think should be understood in terms of relationality, namely, is not relatively to an external context, to a macroscopic world, to a macroscopic apparatus, but systems have properties related to one another. That's, in my view, the best way for making sense of quantum theory. Let me close by saying that the debate is open and the opinions around are different. And I hope I've not given the impression that there is no debate. There is a huge debate around. Thank you.
Oh, that was very, very fantastic.
Thank you.
We have time for questions, but let me just make a few announcements that tomorrow, Carlo is going to be giving the scientific talk at 2 p.m. as part of our regular physics seminar series, black holes, quantum theory, and can black holes become white holes? Or
Nick,
holes?
tomorrow or the day after tomorrow?
It's tomorrow.
Tomorrow, okay.
Yeah. So it's the 28th.
Okay.
And then at noon, we'll just have a light informal discussion, which students, faculty, staff are welcome to come at noon and just chat. There's no set agenda on that. Okay, so there's time for questions, discussions. People want to make some counterpoints, ask some philosophical questions. Again, you could also bring them tomorrow. So speak up. There's a few things in the chat.
I have a question.
Go ahead.
I'm Elizabeth Behrman, by the way. I don't know if you can tell. I want to thank you first for your talk. It was really a nice talk. I think you're maybe a little bit too kind to the other philosophical possibilities of quantum mechanics, because at least with respect to a couple of them, I think, for example, Bohmian physics, the pilot wave thing, is actually wrong. I mean, I think we have experimental evidence that it's wrong, and that's the thing that I'd like you to say a little bit more of, if you would please, and that is that the thing we do in science is not just argue about what is the philosophically coherent thing, but can we actually eliminate hypotheses by saying, okay, this experiment shows that that's wrong. And I think we can do that, for example, with the Bohmian physics. I had a big argument with David Deutsch on the email about, I mean, for example, he thinks that Copenhagen has been experimentally proved wrong. And I think he's wrong, but could you say a little bit about what has actually been experimentally shown to make, for example, Bohmian physics, I think, wrong, and what are the prospects for eliminating some of the other possibilities experimentally?
The physical collapse things keep being tested, and so far all the experimental evidence is against. Why do you say the Bohmian physics has been proven wrong? What you're referring to?
Well, I mean, you have to throw out relativity. I mean, well, okay. I mean, perhaps I should not go that far, but it seems as if the pilot wave idea is just very, very, very unlikely. I mean, as not, maybe not as unlikely as, say, cold fusion, but it's getting there. I mean, I mean, it's so much wishful thinking that the world really were classical. I mean, it's just I don't know. But I mean, wouldn't you like actually to see not just philosophical arguments about whether this or that is more or less coherent and so on, but more oh, okay, we have this experiment which absolutely shows that many worlds can't possibly be right. I can't imagine what such an experiment would entail, but can you say a little bit about possible experimental rulings out of some things?
Yeah, I mean, first of all, I am totally with you. I wish so much we could decide empirically, make an experiment. And let me try to be precise here. definitely that's what we would like. It seems to me that, unfortunately, between these alternatives, we don't have a way of testing experimentally and ruling out, or at least strongly defavoring something. And you just said yourself, no, I fully share your evaluation of pilot wave theory. I am totally with you. I mean, come on. If it pilot wave theory implies that special relativity is wrong.
Yeah,
but careful. Not is wrong in its prediction. It's wrong in its assumptions. Careful, because pilot wave theory gives the same prediction that a special relativistic theory. So it's a pilot wave theory. It's idea that there are some hidden variables, right?
Yeah.
And it's subtle because the hidden part of the wave function, the manifest part of the particle itself. So the behavior of the wave function, which is hidden, does not satisfy general special relativity. In fact, there's instantaneous transmission of information, space-like separation, so in one particular frame. But this is in the hidden part. In the manifest part, it gets cancelled sort of magically. And now, do I believe that? How should I put it? That the good God made the world this way? No, I don't believe it. I mean, do I? No, I don't. I really don't.
You're saying that I'm doing it on the basis of likings and so on also.
No. I'm with you on that, but be careful. But I cannot convince David Albert or Sheldon Goldstein, who are the champions who love this this particular interpretation. And the reason I cannot convince them is because they say, okay, what are the alternatives? And I list alternatives, and each one of them has something strongly counterintuitive in one way or the other.
Like the huge multiplicity of many worlds, or
huge multiplicity of many worlds, or in the relational interpolation, which is the one I like. Now I'm fighting for, so to say.
Yes. Please tell.
There is also some, you have to say, well, are you telling me that by itself this pen doesn't have a position? Yes, I am. So somebody says, come on, right? But this come on is very similar to my come on. I cannot break special relativity in the hidden variables. So quantum mechanics is strange. One way or the other, it forces us to give up something, and we're not sure which one is the one we're giving up. Now, it might be that in the development of science, at some point, one of these vision turns out to be fruitful. Look, when Copernicus wrote his book, De Revolutionibus, the greatest revolution in science, okay?
Yeah, he sold it on the basis that it's calculationally much more more easy.
Well, no, he believed it to be exactly true, but
but he had to sell it that way, and even though he was and he was actually wronger because it was assuming circles.
Yeah, but when the book came out, it came out with a famous preface by Sanger, in which he said, "Look, there's no way of deciding. It's just different ways of making calculations, and there's absolutely no way." No,
it's a great story. Yeah,
it's a great story, and it's who was right? Well, in a sense, everybody was right a little bit, because it's true there is no way of deciding. But it's also true that if you adopt the Copernican perspective, if you take this step, then you can do Huygens, you can do Newton, you can do mechanics. Wow, things you can do.
Yeah.
Wow,
but it's also true that it's actually real. But it's also true that it's actually real. I mean, come on. I mean, the epicycles were actually calculationally much more precisely correct than the Copernican idea on circles. But the Copernican idea was more correct because it was more real. There really is such a thing as objective reality. Come on. You're a scientist. There's an objective reality, yes?
Well, I studied general relativity. That's my which sense is one is more real than the other exactly?
Okay, it actually is true that the planets go around the sun.
No.
Well, okay.
Not true.
All right.
But what is true?
I see
What
your
is
point,
true?
I see your point,
listen.
okay.
What is true is that this way of thinking, it's immensely more productive than the other. It's a better way of organizing reality that works much, much better. There's no doubt. I mean, nobody goes back to.
Okay, I'm going to agree with you, except it's not just much more productive in terms of calculational simplicity and calculational richness. It's also more productive in terms of our understanding of what's going on. And that's the important, that's what I meant by it's more real.
I agree with you.
Maybe the word is bad. Okay, maybe the word is bad. Okay.
I agree with you 100%. And that's, and I hope this is going to happen with quantum mechanics. So somehow like what's happened, I do quantum gravity. That's my job in life, is to do quantum gravity, namely to use quantum mechanics to try to apply to space-time itself. And I think that once you go that way, this relational view, it's viable. The others don't. I mean, if you start breaking Lorentz invariants or multiplying the world, you just get lost into an immense, too much reality out there. It just doesn't make sense.
Yeah. Okay, thank you.
Okay, we saw a hand up. Jason Hildreth?
Yeah, I think we basically touched on my question. Mine was whether the many worlds hypothesis is even a provable or a disprovable theory, since we assume that there's no interactions between the so-called realities. Is that even something that we could theoretically come up with tests for, or is it just something that, if that's your desired framework, that you just have to take on faith at that point?
It's a very good way of posing the question. Let me take out my relational hat and put the hat of a defender of many worlds. I would answer as follows. No, of course it cannot be proved, but do you have a better alternative? Which one?
I don't have a better alternative.
So
I don't know anything.
Yeah, so it's, you see, it's not, you don't, in science you don't prove things. The reality is that you construct a structure, and then the consequences work, and you want the structure to be more or less coherent and comprehensible. And quantum theory is a strange structure because it's not comprehensible and coherent. It doesn't give you a picture of what goes on. So, Newton introduced the notion of force. Can you prove that there are forces? No, you cannot. You can prove there are accelerations, but you can say that there is a force. Well, just force is what he made up. And in fact, in a sense, there are no forces in field theory. So no, you cannot prove that there are other words. But the point is that if there are not other words, what happened when I make a measurement? It's just something. There's no credible alternative according to the many world people, because they don't like the alternative. So the discussion about quantum mechanics, about different perspective, is never how good is it's how bad are everybody else. So everybody adopt a view because find the other one so horrible that it seems that the only alternative is his. And of course, he doesn't see his own defects, like all of us don't usually in life. So the answer to your question is no. There's no way to prove that any worlds. So it's like Elizabeth's question about the Bohmian trajectory. Can we prove that there's a wave and a particle? No.
Okay, other questions, discussions. Again, you might have time to think about this, and then you can come tomorrow at noon when we'll have an informal discussion with Carlo. And then, of course, there's always the chance to listen to his scientific talk at 2 o'clock tomorrow as well. So
to be continued. Thank you very much. And I'm happy to continue this. This is a fascinating discussion, of course, because after all, this is the best theory we have in physics, in spite of its mysteries. So I look forward for seeing you all tomorrow.
all righty. Thanks, everybody. Bye.